Black holes are among the most mysterious and intriguing objects in the universe. They are regions of space-time where gravity is so intense that nothing, not even light, can escape their grasp. Black holes are created from the collapse of massive stars and can grow by absorbing nearby matter. They also play a critical role in shaping galaxies and possibly influencing cosmic evolution. Here's everything known about black holes. A black hole is a region in space where the gravitational field is so strong that the escape velocity exceeds the speed of light. This means that nothing, not even electromagnetic radiation like light, can escape from it once it crosses a boundary known as the event horizon. The event horizon is the point of no return around a black hole. Once something crosses this boundary, it cannot escape the gravitational pull. For an outside observer, time seems to slow down near the event horizon due to the intense gravitational effects described by Einstein's theory of relativity. At the very center of a black hole lies a singularity, a point where gravitational forces compress matter to infinite density, and the laws of physics as we know them break down. All the black hole's mass is concentrated in this infinitesimal point. Black holes typically form in one of the following ways. When a massive star, with a mass greater than 8 times the Sun's mass, exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. Its core collapses under its own gravity, resulting in a supernova explosion. If the remaining core is massive enough, typically over 2 to 3 solar masses, it will collapse into a black hole. Black holes can also grow by pulling in gas, dust, stars, and other material from their surroundings. This material forms an accretion disk around the black hole as it spirals inward, heating up and emitting high-energy radiation, often in the X-ray range, before crossing the event horizon. When two black holes orbit each other, they can lose energy through the emission of gravitational waves. Over time, they spiral closer and eventually merge into a larger black hole, releasing massive amounts of energy in the form of gravitational waves. There are several types of black holes, categorized based on their mass and size. Stellar mass black holes. These black holes have masses ranging from a few to tens of solar masses. One solar mass is the mass of the Sun. They are formed from the collapse of massive stars and are the most common type of black hole in the universe. Supermassive black holes, SMBHs. These black holes have masses ranging from hundreds of thousands to billions of times that of the Sun. They are found at the centers of most galaxies, including our own Milky Way. The exact mechanism for how supermassive black holes form is still uncertain, though they are thought to grow over time through mergers and accretion of mass. Intermediate mass black holes, IMBHs. These black holes are thought to have masses between stellar mass black holes and supermassive black holes, typically in the range of hundreds to thousands of solar masses. While their existence has been theorized, conclusive observational evidence has been elusive. They may form from the merging of smaller black holes or the collapse of massive stars in dense star clusters. Primordial black holes. These are hypothetical black holes that might have formed in the early universe due to fluctuations in density shortly after the Big Bang. If they exist, they could range in size from microscopic to stellar mass objects, though none have been observed yet. The extreme gravitational field near a black hole can bend light and warp space-time, creating effects like gravitational lensing, where light from background objects is distorted. In 1974, physicist Stephen Hawking proposed that black holes are not completely black. Due to quantum effects near the event horizon, black holes can emit Hawking radiation, a form of thermal radiation. Over long timescales, this radiation could cause black holes to lose mass and eventually evaporate, though this process is incredibly slow for large black holes. No-hair theorem. According to this theorem, black holes can be completely described by just 3 observable properties: mass, electric charge, and angular momentum, spin. This implies that other characteristics, such as the internal structure of the matter that collapsed to form the black hole, are not observable. Tidal forces. Near the event horizon of a black hole, the gravitational gradient is so strong that it can cause spaghettification, where objects are stretched into long, thin shapes as they are pulled into the black hole. This is especially pronounced in smaller black holes, where tidal forces near the event horizon are stronger. While black holes cannot be observed directly, since no light escapes them, several methods are used to detect and study them. X-ray emissions. Material that is pulled into a black hole forms an accretion disk that heats up and emits X-rays as it spirals inward. These X-ray emissions can be detected by telescopes such as the Chandra X-ray Observatory and XMM Newton. When two black holes merge, they emit gravitational waves, ripples in spacetime that can be detected by observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo. These detections have provided direct evidence of black hole mergers. In 2019, the Event Horizon Telescope, EHT, produced the first-ever image of a black hole's shadow, which is the dark region caused by the event horizon against the backdrop of glowing material. This image showed the supermassive black hole at the center of the galaxy M87. Black holes influence the orbits of nearby stars and other objects. By observing these orbits, astronomers can infer the presence of a black hole. For example, the stars orbiting the center of the Milky Way provide evidence for the existence of Sagittarius A*, a supermassive black hole at the galaxy's core. Sagittarius A*. This is the supermassive black hole located at the center of our Milky Way galaxy. It has a mass of about 4.3 million times that of the Sun and is surrounded by a dense cluster of stars. Cygnus X-1. One of the first black hole candidates discovered, Cygnus X-1 is a stellar mass black hole in a binary system, where it accretes material from a companion star. It is one of the strongest X-ray sources observed in the sky. M87's black hole. The black hole in the galaxy M87, which was imaged by the Event Horizon Telescope, is one of the largest known supermassive black holes, with a mass of about 6.5 billion solar masses. Black holes are not just fascinating due to their extreme nature, but also because of the profound impact they have on their environments and the larger universe. Supermassive black holes are thought to exist at the centers of most galaxies, and they likely play a role in galaxy formation and evolution. The relationship between a galaxy's central black hole and its stellar bulge, known as the M-sigma relation, suggests a coevolution of black holes and galaxies. Some supermassive black holes at the centers of galaxies are surrounded by large amounts of infalling material, forming active galactic nuclei. When material spirals into the black hole, it emits huge amounts of energy, sometimes outshining the entire host galaxy. The most extreme examples are quasars, which are powered by supermassive black holes. Some black holes, particularly in active galaxies, emit powerful jets of high-energy particles that can extend far beyond the host galaxy. These jets can regulate star formation and influence the intergalactic medium. Information paradox. According to classical physics, any information that falls into a black hole is lost forever. However, quantum mechanics suggests that information should be conserved. This leads to a paradox that is still unresolved, though various theories like holography and firewalls attempt to address it. Wormholes and time travel. In some solutions to Einstein's equations, black holes could connect to other points in spacetime via wormholes. While purely speculative, these ideas suggest that black holes might allow for exotic phenomena like time travel or connections to other universes. Black holes are some of the most enigmatic objects in the universe. From their formation through the collapse of massive stars to their potential role in galaxy formation and cosmic evolution, they challenge our understanding of the fundamental laws of physics. While much has been learned about black holes, many mysteries remain, particularly regarding their quantum nature and the behavior of matter at their singularities. As our observational techniques improve, black holes will likely continue to reveal new and unexpected insights into the workings of the universe.